Okay, so that is Math 400 Lecture 12, Random Variables 9, Poisson Distribution, and this is the differential equations approach. So let nt be the number of people entering the bank in the time interval 0t. Well, you might say, what is 0t? It means that you have like a stopwatch and it starts at 0, right? So, and we use this small p nt as the probability that nt, which means the number of people entering during this time period, is n. So this is probability that in this time period n people arrive. And we also make an assumption, or in fact some assumptions. So given that lambda people enter the bank in the time period 0, 1, that's the assumption we have, we make the following assumptions. There exists a time period 0 tau, such that's the time period I discussed last time, such that the probability that in this time period only one person arrives is lambda tau, and the probability that in this time period more than one arrives is 0. So in this time period, either one person arrives or nothing, 0. And the number of people arriving in adjacent periods of time are independent. So if from 0 to 5 minutes, for example, some people arrive, then from 5 to 20, the number of people arriving in the adjacent time interval is independent from the one that arrived from 0 to 5. So from 0 to 5 and from 5 to 20 or 5 to 5 point something, whatever, they are independent. Okay, so let's continue with these assumptions and these notations and come up with some nice formula for this thing, PNT. That's what we want to find, right? PNT is in fact what we are trying to find. So let me erase this. So we have the P of n of tau equals 1 is lambda tau. So we only have 0 or 1. So P of n tau equals 0, that is the complement of this. This event, if this is E, this is E C. That's the complement of this, because there is nothing more than 1. More than 1 is 0. So if this is the complement, then it is 1 minus lambda. Okay. So if that is the complement, that is 1 minus lambda tau. Now we do this. So what is P of n of t plus tau being, say, n plus 1? What is t plus tau? T plus tau is you start at tau and go to t plus tau, right? You're adding t. So that's from 0 to, you see it goes from 0 to t plus tau. So you have 0 here, tau here, and then t here, this is t plus tau, right? So if this time interval has length t, then that's t plus tau. Now I use those assumptions to come up with something here, something interesting. So I look at this. This is in fact P of, say, n of t plus tau, n of t, in fact, is n plus 1. N plus 1 minus, let's say, k. So let's, how should I write it? So let's write it like this. This is K, and N tau is K. Okay? So I can do it like that. When you see in this time period from 0 to tau, then from tau to t plus tau, I'm trying to find a probability of this thing being n plus 1. I can say, okay, I can divide it in two parts, saying that nobody arrived here and n plus 1 happened here. 0 and n plus 1 people arrived here. One person arrived here and n plus 1 minus 1 arrived here. 2 arrived here, n plus 1 minus 2 arrived here. So I can do that. This is a legit assumption that in this small time period, nobody arrived and then n plus 1 arrived here. One person arrived here and n plus 1 minus 1 arrived here. 2 arrived here, then n plus 1 minus 2 arrived here. Okay? So I can write it like this, and then this K, so this event itself, this and this, is an event which depends on K. And how many such events do I have? And they are independent, right? They are mutually exclusive. So this whole thing will become the sum of these things. And K goes from 0 to, assuming that all of them happen at n plus 1, right? So again, K goes to from 0, nobody arrives in the first time period, up to all of them arrive in the time period 0 to tau. And these are mutually exclusive. At any, say, configuration, one of them happens, so they are mutually exclusive, and these are independent. Remember, that was the third assumption, that what happens in one time interval is independent of the other, what happens in the other time interval. So having K here is independent of having n plus 1 minus K here. So the first one will give me this sigma, that they are mutually exclusive. The second one will give me a product here. So I will get K from 0 to n plus 1, and the product of these two, P of nt is n plus 1 minus K times P of n tau is K. Right? P of n tau is K. But look over there. N tau being bigger than 1 is 0. So K can only be 0 and 1. 0 and 1. So just two of them stay alive. P of n t is n plus 1 minus 0. P of n tau is 0 plus P of n t is n plus 1 minus 1 times P of n tau is 1. Okay, so let me continue here, right? So I can just write it down as P of, what is this one? This one, by that formula, is Pn plus 1 of t, right? This one is Pn plus 1 of t. And times what? Times this. 1 minus lambda tau. Then this one is Pn of t times lambda tau. This is lambda. Okay? So, okay, so that is, now let's put them together, and if I put them together, I will get this. So this is Pn plus 1, Pn plus 1 of t plus tau, right? So if I put them together, I will get this. Pn plus 1, t plus tau, minus Pn plus 1, t, over tau, in fact, equals this. Just put them together, minus, let me copy from what I have here, lambda times Pn plus 1 of t minus P of t. Okay? So this is equivalent to this, just to put them together, so I can see that here. So I have a Pn plus 1t times 1. If you move it here, then you can divide it by tau, and you get this. Right, it's very simple. Now, what do you see here? Those of you who remember Calc 1, this is like what? This is like h over h. Remember, what was the derivative? Derivative was, remember, f prime x was defined as limit as h goes to 0, f of x plus h minus f of x divided by h. So what if I set limit as tau goes to 0? There is no tau on the other side. Right? This doesn't depend on tau. On this side, there is no tau. So in the limit, it's the same thing. You see, if it doesn't depend on tau, then the limit is also the same thing. So if I say limit as tau goes to 0, this side doesn't change, because limit as tau goes to 0, this is itself. It doesn't depend on tau. But what is this side? This side will be dPn plus 1 of t by dt. That's derivative, right? So I have come up with this a nice differential equation, minus lambda. But it's not one differential equation. Those of you who have taken differential equations, you can see that it is like a system of differential equations. But it's a very simple one. You can solve it. And so let me write this differential equation up here. So I have come up with this nice differential equation, dPn plus 1 t by dt is minus lambda times Pn plus 1t minus Pnt, and this goes down to dP0 of t by dt. There is no Pn minus 1, so it's minus lambda P0 of t. Now this one is very simple, right? That's e to the power minus lambda t, in fact. This one is very simple, and you can just find this, then go back and find P1, then P2, P3 up to Pn plus 1. But then, yeah, and that will give you the whole, say, picture of the Poisson distribution. So that is the differential equation form, and that's how you derive this differential equation. In fact, system of differential equations, not just one differential equation. Okay, so that was the story of Poisson. I do not intend to discuss the Poisson process. You can read that from the book, because the Poisson process needs also exponential process or exponential distribution. So I will discuss it when I go through that exponential distribution, which comes in the next chapter, in fact. So I guess that's enough for now, and see you next time.